Hello, ladies and gentlemen. I am Yuexia from Tianjin University, China. It's my great honor to share with you on a study in elementary schools. The study is about indoor environment in classroom and its association with students' respiratory infections. The presentation has the following 4 parts of contents. You may wonder why we focus on indoor environment in schools. First of all, classrooms in elementary schools have high occupancy levels. In China, usually 40 students share one classroom with a size of 50 to 80 square meters. In such crowded spaces, students have very frequent close contact. Classrooms in elementary schools in China have natural ventilation systems. That means we have limited access to fresh outdoor air, especially when the doors and windows are tightly closed in winter. Students spend most of their time in schools. Therefore, school environment must have a very important influence to their health. Additionally, occupants in these classrooms are children. They are under 13 years old. Their physical, mental, and immune systems are under development. Those students are sensitive to indoor pollutants. Therefore, we focus on school environment and students' health. To be more specific, we focus on respiratory infections among students. So our study started with literature review to understand the current status of indoor pollution in school environment. Then we performed field measurement on environmental parameters and collect data on health outcomes. We have on-site measurement from aldehyde, TVOC, benzene, toluene, xylene, and ultrafine particles. We also have online continuous measurement on CO2 temperature, relative humidity, ventilation rate, and PM2.5. The health outcomes are respiratory infections and the consequent absence rate. Finally, we use model to study associations between environmental factors and infections and to predict infection rate. We invited 10 schools to join our study. Those schools are all located in northeast China with cold winter climate. Those schools have the same heating period from November to March. There are no obvious outdoor pollution sources such as plants or factories around those schools. The location of those schools cover urban, suburban, and rural areas. Classrooms in those schools are all naturally ventilated. As shown in this slide, on-site measurement of ultrafine particles from aldehyde TVOC were measured by portable instruments. The concentration of benzene, toluene, and xylene were identified through air sampling and the GCMS method. The concentration of CO2, air temperature, relative humidity, and PM2.5 were monitored by sensors installed in classrooms. The online data was transferred to a hub and downloaded by researchers through internet. The respiratory infection rates and the consequent absence rate were reported by teachers every day. Our study was performed since winter in 2018 until now. In total, 47 classes in 10 schools joined our study. Among them, 27 classrooms for second grade and 20 for fifth grade. Students in these 47 classrooms were all involved in our study and resulted a total number of 2,020 students. Among those participated students, 369 in urban area, while 926 in suburban and 725 in rural areas. The school hours for all the students are basically the same, with an average of 9 hours per day, 5 days per week. The on-site measurement on VOCs and ultrafine particles are summarized here. The concentration of formaldehyde and VOCs are all below the reference levels recommended by Chinese IAQ standard. Rural area had relatively higher concentration of VOCs and formaldehyde compared to those in urban and suburban areas. With regard to seasonal variations, winter had higher concentration of those pollutants compared to other seasons. We have online continuous monitoring on indoor PM 2.5 of temperature, relative humidity, and CO2 concentrations. The CO2 concentrations are used to estimate ventilation rate, either in air change rate per hour or liter per second per person. We exclude measurements in holidays, vacations, and weekend from data analysis. Finally, the valid samples are 4,500. In the following slides, we are going to present the results of online measurements with regard to pollutants distribution in different areas and different seasons. So first, let's look at PM 2.5. More than 85% of the valid samples had daily PM 2.5 concentrations below the Chinese standard of 75 microgram per cubic meters. Rural area had the highest concentration of PM 2.5 with a median value of 38 microgram per cubic meter. The reason for the high concentration in rural area may be that, firstly, 2 schools in rural were closed to highways. Vehicle exhaust and road dust may cause high concentration of indoor PM 2.5. Secondly, from the perspective of indoor sources, the class occupancy level in rural schools is larger than that in urban and suburban. Let's say 55 people share per room in rural area, while it's about 37 in urban and suburban. Therefore, indoor disturbance may be greater in rural than in other two areas. This may cause higher PM 2.5 concentration indoors. The distribution of PM 2.5 also had a significant seasonal variation. In winter, higher concentration of PM 2.5 were monitored, followed by autumn and summer. This is the same as that of most cities in North China. Now let's look at the temperature distribution. Generally speaking, the room temperature ranged from 40 degrees to 33 degrees with an average value of 23. The seasonal distribution of indoor air temperature shows that we had highest temperature in summer, lowest in winter, spring and autumn in the middle. All the classrooms we have monitored had a natural ventilation system. There is no air conditioner. Thus, these indoor temperature variations may reflect the outdoor air variation in different seasons. Urban area consistently had the relatively higher temperatures than suburban and rural. This may reflect the heat island phenomenon in urban. The next is relative humidity. The indoor daily average relative humidity ranged from 10% to 77%, with an average value of 37%. The same as indoor air temperature, the indoor air relative humidity also had the highest value in summer and lowest in winter. It's interesting to notice that in winter, indoor relative humidity in rural classrooms was significantly higher than those in urban and suburban. This may be due to that, as I have mentioned before, rural classrooms had higher occupancy level, like 55 people share per room, and in other areas is only 37. The poor ventilation in winter may not efficiently remove the extra moisture from occupants in rural areas, therefore resulting in higher relative humidity. So the question is, how is the ventilation condition in classrooms? This slide shows the CO2 concentration in classrooms in Chinese elementary schools. The CO2 concentration in a way reflects the ventilation conditions. The result on CO2 measurement is shocking. As we see here, the indoor daily average CO2 concentration ranged from 400 ppm to 4000 ppm, with an average of concentration 2000 ppm. 85% of the samples exceed the 1000 ppm, which is the acceptable level in a Chinese and international standard. Winter had the highest indoor CO2 concentrations. The average daily value was 2,300 ppm. In winter, 97% of samples were above 1,000 ppm, the reference value in standard. CO2 concentrations in rural classrooms was the highest. This may be due to its overcrowded occupancy level in this area. Based on CO2 concentration, we had chance to calculate air change rate in the investigated classrooms. The daily air change rate varied from 0.01 times per hour to 11 times per hour, with a median value of 0.8 times per hour. This value is much lower than the value recommended by Chinese standard. In the Chinese hygiene standard for classroom, the minimum air change rate is recommended at 3 times per hour. In our study, only 8% of samples met this standard. The seasonal distribution of air change rate shows that it varied greatly in summer, while in winter the air change rate was relatively concentrated. Let's say the median air change rate in spring is 1 time per hour. In summer, it was 2 times per hour. Autumn, 0.9 times per hour. Winter, 0.5 times per hour. All the investigated classrooms had natural ventilation system, which depended on opening windows and doors to have fresh air. In winter, people want to keep thermal comfort indoors. Doors and windows were tightly closed. Therefore, the air change rate is extremely low in winter, as I mentioned here, 0.5 times per hour. Almost none samples in winter met the Chinese standard of 3 times per hour for air change rate. Considering the high occupancy level in classrooms, how much fresh air can be provided to each student? According to Chinese standard for each person, at every second, there should be 6 liters of fresh air be provided. However, the real-life condition is that, in general, we only have fresh air of 1 liter per second per person in classroom. Only 4% of samples met the recommended values. In winter, no classroom was able to meet the minimum recommended value. In such crowded spaces with very limited ventilation, how is well-being and the daily attendance rate of students? This slide shows the absence rate of investigated students in schools. The absence rate due to respiratory infections among students were reported by teachers. It shows that the average daily absence rate is 1% per day. Winter had higher absence rate. In the next step, we use zero-inflated negative binomial model. We call it ZINB model to study the associations between school environment and respiratory infections. Firstly, the environmental parameters in day 1 through day 7 were combined to calculate an average index. Then this parameter index was associated to the respiratory infection rate in day 8. The 7-day period was chosen because this is the incubation period of some infection pathogens, such as rhinovirus, influenza virus, and show air variables that influence virus survival, transmission, and host susceptibility were considered in the ZINB model. 2 metrics of ventilation was considered in the model. One is air change rate per hour, the other is liter per second per person. This slide shows the associations between indoor environmental parameters and absence rate due to infections. In the zero inflation model, relative humidity had a significant negative impact on infections. In the negative binomial part, temperature, relative humidity, and ventilation were statistically significant. The higher temperature, the higher relative humidity, and the higher ventilation rate, then we observed lower percent of absence rate in each class. Let's say the temperature increased by 1 degree, then the absence rate would reduce by 12%. 1% increase in relative humidity, 5% reduction in absence rate. The strongest influence is from ventilation. An increase of 1 time per hour of air change rate would reduce absence rate by 30%. The same significant influence on absence rate was observed with another ventilation metric, liter per second per person. It also shows that if we have air change rate increase 1 liter per second per person, then the absence rate due to respiratory infection would be reduced by 22%. Conclusions. We performed this study since 2018. To our knowledge, this is the first study that has such long-term measurement, both on ventilation, other indoor environment parameters, and same time we collect data on respiratory infections. The results are very shocking. So, average CO2 concentration in classrooms are 2000 ppm. The ventilation rate can be as long as 0.5 per hour or 1 liter per second per person in such overcrowded classrooms. Most students were exposed to adequate ventilation rate in classroom, and this inadequate ventilation increased the absence rate due to respiratory infections. I hope you are still with me, and I hope to work with you together because we need to improve the indoor environment in classroom. We need to provide healthy air to establish a healthy school environment. And thank you for your listening. I would love to hear from you on your advice. Please contact me for any comments. Thank you very much.